So, dear friends, I think we should more or less finish our lectures. So, plans were big, but not all the things I wanted to discuss we have discussed, so it's life. But nevertheless, we have plenty of problems for examination, and also I have problems which I immediately exchange for excellent marks. So if you are able to solve these problems, you will be happy. Me too. So we start from reminder from physics. What is the Dirac equation? We will not use it. Nevertheless, we want to look at this. So guys who study physics already know what is it. Guys from Department of Mathematics maybe will be a little bit surprised. The formula is this one is a Dirac operator, and if we add here minus mass term times psi equal to 0, this is a Dirac equation.
Minus sign.
Where? Here?
Yes.
No, it depends on the sign here. Okay. For your pleasure, we add plus and minus. So what is strange here? What is strange here? Let me read. Plus minus I gamma mu d over dx mu. See? Okay, that's all. The question is, what is written here? What is gamma mu? Gamma mu is a matrix, matrices which satisfy very interesting property. Okay, plus minus. So if we consider anti-commutator gamma mu times gamma nu plus gamma nu gamma mu, anti-commutator, on the right hand side we obtain a plus minus, it depends on your preferred choice of sign, 2 metric tensor of Minkowski space. Then Paul Dirac was trying to find the linear operator, which should be something like square root from Laplacian. He found that he can do it for Minkowski space, provided he knows what is gamma. But now you know what is gamma. What is gamma? An element of Clifford algebra, because this is a relation from Clifford algebra. Dirac himself said that these things are just 4x4 matrices. Gamma mu is 4x4 matrix. And psi is a function which consists of 4 components. So spinor in his thinking was 4-component spinor. So since many times have passed, huh?
There are 2 components.
What do you mean by that?
The dimension of matrices depends on dimension of space-time.
We speak about electron.
Yes.
So sometimes people split it into gradient and contragradient representation, but don't think about it. So we already saw it on the modern language. Then we spoke about spinor representation of spinor group and so on, so on. We saw generalization of this guy to contemporary mathematics and physics. So let us go. So let me give you general geometric setting in which this thing appears as geometric Dirac operator. Geometric Dirac operator. So assume M and G is a Riemannian manifold. So we have manifold and metric on it. For sure we have connection. Maybe we want to add here that this connection is Levi-Civita connection, so null is null G or Riemannian connection. What we can do with that? We can apply construction. So how we construct Clifford algebra? So we have vector space and scalar product in it. From that we constructed Clifford algebra. Okay, assume we have an isometry. So if we have V1 first scalar product and F is isometry of two vector spaces, it provides us isomorphism. Isomorphism of algebras.
F is isometry.
F is isometry, yes. Otherwise, relations are broken. We need to keep relations. That's why it's isometry. This very simple algebraic idea gives us possibility to apply construction. So this is construction from the algebra. Yes, we construct algebra from vector space. We can apply Q as a functor to cotangent bundle. Take a cotangent bundle with a metric induced here. So we have metric on tangent bundle, so we have another metric on cotangent bundle. So we can apply here Cliffordization. We apply functor Q to each fiber. And this idea means that it's compatible with change of coordinates in fibers. So from that we obtain Q of M, which means we apply fiber-wise construction. It is a vector bundle.
So it's classical gluing, yes?
Yes, just so you take gluing cocycle for this guy, apply this thing on intersections, and you obtain just isomorphisms of Clifford algebras on overlaps. So this is a vector bundle of which rank? Which is the dimension of the fiber?
Two in power of dimension.
Yes. Rank is equal to 2 to the power of dimension. But it's not a vector bundle, it's a vector bundle of algebras. It's bundle of algebras. And the multiplication, fiber-wise multiplication is continuous and so on. So you can consider sections, multiply the sections, and so on. A very important thing. It is a substitution for the collection of gamma mu. Because inside this guy, cotangent bundle sits inside this object as generators. Okay, so now we pass to the understanding what, so psi here is just spinors, but we will consider this in vector bundle setting. So let me give you several definitions. S bundle, super bundle. It's a very simple thing. It is a bundle over M such that E is represented as a direct sum, Whitney sum of two bundles, E plus and E minus, even part and odd part. What is a Clifford bundle? Clifford bundle, very important thing. Clifford bundle, or Q-M module. It's not very correct way of saying, but nevertheless we can think that it's vector bundle, Clifford bundle. It's a vector bundle on which this guy acts from the left. So for example, you can take sections of this bundle, take sections of this bundle, and fiber-wise action of this thing here gives you a new section of this bundle. So what is it? It is a S bundle plus a bunch of data, Hermitian metric, plus connection, nabla e. Okay. Preserves Z to grading. It means that if you take a section of E plus and apply connection, then you still obtain a section of E plus, and you do the same for E minus, then the same happens. Maybe we can write it in this way, that covariant derivative of sections of E plus minus preserves type of section. Tell me please, who is Xi?
Tangent.
Tangent vector space. Vector field. Section of Tm. Okay. Hermitian.
So it's definitions, yes?
It's still definition. It's not finished yet. Hermitian connection. And important formula. Well, I forgot to say that. Well, sorry. It is I'm going too fast.
I would assume that Clifford bundle is just sheaf of full M modules, no? Are these
If you say that it's sheaf of it's a constant stocks, or how to say, constant fiber with the same fibers at each point, it would be.
It's sheaf of modules of over local M.
Of course, because you take sections of this thing and
No,
sections of Clifford acts on.
Yes, but
it's locally free of constant rank, and if you consider sheaf, it can be, it can have jump of directions. You can think about it as a sheaf, yes. Let me correct my definition. So Clifford bundle, it is S bundle with plus morphism. From what? From col of M to endomorphisms, graded endomorphisms of E. This thing will be denoted by C. And what is important here, that C of A, which acts on E, is skew symmetric with respect to Hermitian structure. Where alpha is a section of cotangent bundle. Is it correct?
so we do ask that E has metric.
Yes. S bundle plus Hermitian metric. I tried to group some pieces of definition into several pieces. So S bundle is bundle which is represented as a Whitney sum of two subbundles. Clifford bundle, it is a bundle which is equipped with action of this guy. Yes? This means that if you take, so in Clifford M, there are sections of cotangent bundle, so cotangent bundle changes pairing, changes sign here, because endomorphisms here are graded, so with hat. So C alpha maps sections of E plus minus to sections of minus plus. Yes, and now I say what is Dirac bundle. because there are several structures here. So you need to have splitting, you need action, and now you need to choose a connection here. The connection here is a new data which is more or less independent of this guy, of this data, but connection here should be related to all previous things in a very explicit way. So we take E and connection here. What we say about this? E is a Clifford bundle. So everything what was written before. Nabla E is a Hermitian connection which preserves Z2 grading. Now I write the formula which I erased. So if you take a covariant derivative with along vector field xi, xi belongs to vector fields on base manifold, then the sections of E plus minus go to sections of E plus minus, not changing a sign. So the only we need one formula which relates connection here with action of Clifford Clifford bundle, because everything else is fixed. So assume alpha is a section of cotangent bundle. So this guy sits in sections of what? Of Clifford. If I know the relation, how this thing is related to connection, then everything will be okay. So assume I want to calculate nabla of E on the section which has the following form: C alpha dot U. U belongs to sections of E. Let's check what is written here. I have section of my vector bundle E. Alpha is an element from sections here. I write here C of alpha, so C of alpha is endomorphism of E. So this thing which is written here is a section of E. Let me denote it, that is just section of E. I do not know about parity, but look here. Actually, we have here a product. Here we have a product, because this is a section of one thing, it's a section of another thing, it's action. So if we write it in local charts, it will be matrix times vector, so it's a product. So we need to have here something like Leibniz rule. Okay. So we need to take a derivative of alpha. Okay, alpha belongs to, it's related to M, nothing to E, so we take metric connection, so Levi-Civita, and apply it to alpha. It is, now we write here C, and this thing is applied to the section U. Are we happy with this formula? Not yet, because there should be another summand. Okay, which one? Very simple. C of alpha acts on nabla E applied to U. I would say that I'm also not happy about this formula for the following reason. Because covariant derivative maps sections of one bundle to sections of another bundle. And then I need to understand what does it mean that this guy acts on the section of... You see, alpha, it is a section of cotangent bundle. Nabla of alpha is a section of what? Cotangent bundle, tensor to cotangent bundle. How this guy should act on U? Nobody knows. So we add here vector field and apply it here. So it's covariant derivative, it maps sections of one bundle to the sections of the same bundle. So we don't worry about that. And you know that if we write covariant derivative, everything which is written here is just linear in xi. So we don't worry about it. So xi is not under derivation here. So just linear operator with respect to xi. So this is formula which relates everything here. Good. We need an example. We need an example. I will give you an example. Very important. Very simple. Important example. So we spoke about Dirac operators previously. What was an example of Dirac operator? We had one. Hodge-Deram, yes. So, as E, we take exterior power of cotangent bundle. The splitting is very simple. E is lambda even lambda odd. For simplicity, I will write here lambda even and lambda odd. Okay, so now I need to say how Clifford acts here. Okay, connection on M induces connections on lambda even plus lambda odd. Because it's just differential forms, so if you know how to derive the formula for covariant derivative for tangent vectors, cotangent vectors, so you know what how to define covariant derivative of sections of this bundle. The definition is not erased. Tell me, please, what we need to define further. Splitting is given, Hermitian metric is obvious. Oh, we need morphism. We need to map Clifford to endomorphisms of exterior algebra. Okay. Consider C, which sends to E. In which way? So we don't want to consider all Clifford bundle because it's too complicated. We consider alpha, which belongs to omega 1 of M, which is a part of sections of Clifford M. Yes? Very important question. I hope you remember how alpha acts on differential forms. So C alpha applied to differential form, there is an explicit formula how to act in a Clifford way by alpha on differential form.
VUH on W plus V.
More or less, yes. So, yes, there are two summands. First of all, we take exterior product of alpha with differential form omega. This is in case then omega does not contain alpha as a part, as a term inside it. And also we write here minus interior product alpha dagger applied to omega. What does it mean? Alpha dagger. The metric dual to alpha. Because we have metrics, so we have identification of tangent and cotangent sections. So this is a metric dual. That is a vector field. Alpha dagger is a vector field. Because we need to take a contraction of differential form with something to decrease the degree of form by 1. It can be done in one way. So substitute there a vector. So this is an action. We defined it. What else? Yes, obviously this guy changed parity, because if omega was even form, then these and these are odd forms, but of different degree. But so that's why we cannot split it further, because these two summands have different degrees. But if this one left-hand side omega was even, then right-hand side is odd, and vice versa. So we need to. Everything is okay. We have a setting which is written here. Everything is okay. But what is left? What is left? Only one thing is left. It will be your exercise to check that the identity star is true. Check. Check identity star for this case. An exercise in differential geometry, not very difficult.
And maybe also that covariant derivative on E preserves grading, or is it obvious?
Covariant derivative of, I think it's obvious, because if you take, so what you are doing then, you take covariant derivative of differential form. You write some expression which is of the same degree.
It's by construction.
Just by construction, nothing else. It's not. It's obvious. Well, okay. We did it. So now we should define. Well, I forget to say what is important. C of alpha should be skew symmetric. It's another exercise. Check C alpha is skew symmetric. It should not be very difficult, so it's okay. Well, so we have everything to define Dirac operator in general setting. The general setting is as follows. So what we are doing, we consider sections of E. Then we take covariant derivative. Not a long vector field, just genuine covariant derivative, and we obtain sections of what? It's true? It's true. But you consider this part as a sub-bundle in Clifford bundle. So if you have a section of this bundle, you can consider the section of this thing and this thing. So further you apply Clifford action and obtain gamma E. That's all. This composition is, I will write it in this way. I'm not sure that I can write it in a calligraphic way, but I'll try. This is D calligraphic. Maybe I need to add here some letter. DE.
So, can I ask a stupid question? So the second arrow goes to gamma endomorphism tensor E, and then we evaluate and get section.
Sorry?
So the cotangent bundle
Is part of here.
is part of here, and we have also
Yes.
the tensor E. So we
Yes.
So we go to
So this guy is exchanged.
endomorphism tensor.
Yes, and then you apply matrix here. Okay. Yeah.
Evaluate.
Yes. Yes. Exactly. It's exactly what is written here. This thing is exactly what is written here. In coordinate-free way. Just think about that. I'm not lying. It's true. What is written here is written here.
Where the mass can appear?
Sorry?
Where the mass?
No. Mass is not a part of Dirac operator. Dirac operator is this part. Well, so another exercise. I don't know. I think it's more or less difficult. Maybe not. Exercise. In our example, D, D, this one, which is calligraphic D, is Hodge-Deram operator, D plus D star. So just check that in this case, Dirac operator, geometric Dirac operator is exactly Hodge-Deram operator. Okay? Yes, and in this case, this is...
So we define Dirac operators on Dirac bundles.
Yes. So you take geometric data, which actually is a very simple thing. Clifford, bundle of Clifford algebras is always exists if you consider manifold with metric. But the question is where it acts. Where it acts. So you need to prepare some specific Dirac bundles. The simplest way is take differential forms and split it in this way. Another situation is then you split the same vector bundle in different way, having volume form. In this case, you will obtain the same formalism, but the splitting will be different, and the index of the Dirac operator will be different. And you obtain another invariant of the manifold. I will tell you about it. But there are other interesting questions. Then you consider not this vector bundle E, but constructed from topological data. For example, it can happen that manifold M is a spinor bundle, and it has much more interesting collection of vector bundles with action of Clifford algebra. Spinor bundles. Spinor bundles. And then you obtain some other invariants of the manifold.
And in that example, in coordinate form, what is...
Sorry? Here?
Yes. Above. It's for any E.
No. This example was in a specific setting because manifold is a Minkowski space.
Which is E for this specific setting?
Spinor bundle.
Okay.
On Minkowski space.
Okay.
There's a nice question. Spinor bundle. It's trivial because it's Minkowski space, but the action is not so stupid as written here. It's spinor. It's action by spinor group. Okay.
So exercise is that Dirac operator is Hodge-Deram operator.
In this case, yes. Well, to be accurate, let us check that Dirac operator, that it will be of this form, it does not depend on splitting, because I didn't use splitting in this definition. Okay. Splitting needed for the following reason. This operator is self-adjoint. If you look to this operator, it's self-adjoint, its index is 0. Index of this operator is just 0. That's why we need splitting. Let me erase here, and I will tell you what happens further. So in splitting of our form, look here, this map preserves parity, yes? And this map changes parity. Action by C changes parity. That's why this guy can be written in the form, in the splitting. So you write here DE plus DE minus 0. So these two operators do the following. They map sections of E plus minus to sections of E minus plus, and if you look to the sections of well, I think it doesn't, this plus doesn't act on sections of minus, so it goes to 0. So it's block matrix here. Moreover, D plus minus E, formal adjoint is D minus plus of E. So in this case, when people says about index of this operator, they have in mind graded index. And how people write it. So then people say about index of Dirac operator that people mean the following thing. They take index of D plus part, which is dimension of kernel of D plus, minus dimension of kernel of its adjoint. This is a definition. So you have geometric situation, you have vector bundle, action of Clifford bundle, a bunch of connections, blah, blah, blah. You obtain Dirac operator, but to calculate its index, you need splitting. You need to have splitting of vector bundle into two subbundles such that other properties are satisfied. And now I can tell you what are the exercises which I exchange for excellent mark. But be careful, only 2 first persons on each problem can obtain excellent marks. So 6 person at maximum. Because we know that if 2 persons in Department of Mechanics and Mathematics know how to solve the problem, everybody knows how to solve the problem. At least they know what to say to assure the professor that they know how to solve the problem. Okay, first question is very simple. So every question consists of 2 parts. First question is very, very simple. What is an index of Hodge-de-Rham operator? Actually, it is equal to Euler characteristic of manifold M. Not difficult, but we already talked about that. But what is interesting here, calculate right. Oh well, so in the right-hand side of Atiyah-Zinger formula, you will see integral of Euler class. I will write you general formula for Atiyah-Zinger theorem, and the right-hand side in general situation is very complicated, but it can be, in each particular case, it can be simplified. So in the case of Hodge-de-Rham operator in this splitting, index is Euler characteristic, but the right-hand side of Atiyah-Zinger theorem independently can be reduced to Euler class, which is defined in terms of curvature, some differential form, blah, blah, blah. Second question is more difficult because how to split by volume form for dimension of M. Okay, let it will be even. So you need to check the literature. Maybe you can look at Wikipedia and some other sources, but maybe some beautiful textbooks from the previous century. How to split this to obtain the formula that index of Hodge-de-Rham, same operator, but splitting is different from that one. It means that index will be different because then you split in another way. You take dimension of another kernel minus dimension of another kernel. It will be different number. But I will tell you the answer. It is a signature of the manifold. If you don't know what a signature of a manifold, you can learn it. It's not difficult. Well, to be honest, the signature is well defined for dimension of M is 4M. Signature is a signature of intersection form in the middle dimension of cohomology. So if it's 4m, then that intersection form is symmetric. Okay, it's simple part, it's not difficult. What is interesting, in the right-hand side of Atiyah-Zinger theorem, you will see another differential form. It is denoted by L. It is Hirzebruch genus. So in general form of Atiyah-Zinger theorem, there will be same expression for this case, that case, and the case I will say a little bit later. But for this splitting, the general expression should be simplified to this form. How to simplify it, you will find. It's not very difficult, but it takes time. And last question is about what? So okay, M is 4-dimensional, 4m dimensional in this spinner. We have not discussed what is it. That's why this problem also costs excellent mark. So you can check what is spinner manifold, then find spinner E. It is not constructed from differential forms, it's constructed from spinner structure. It's a very interesting thing. It's not very difficult, but it's very, very interesting. Well, and then you calculate index of corresponding D, E plus. There are no simple expression for that guy. So index of this operator is just the value of the integral. And integral will be a hat genus of M. Yes. So there is a specific differential form which can be denoted in this way. Then you evaluate it on M, you obtain a number. This number is a hat genus of M. Very important thing. Okay? So you find explicit expression for a hat.
So could you again repeat what is to find spinner E?
No. Take a literature and read what is written there. There are no way to guess what is it.
So this
you have no time to.
We're not supposed to.
You are not supposed to guess. You have no time for that. I guess you are very clever guys, and you can introduce every notion in mathematics if you have sufficiently much time. But you have a session. You have to pass exams.
For example, 100 lives.
Yes, no, well, I think for maybe 10,000, because many people worked in this field. Yes, imagine you can live all their lives, then I guess that at one moment you will know what is it. At least then you live life of Elie Cartan, you will know what is it. You will invent it. So just find it in literature and learn the details of the construction.
So the excellent mark will stem from either or from all of them?
No, from either of them.
From
one problem,
okay.
and well, but 2 persons for one problem at maximum. Okay, so what is the right-hand side of Atiyah-Zinger theorem? Let us discuss what is written there. I erase it. So index of the operator is the integral over M of the following differential form, a hat M G. Then you write specific version of Chern character. Of what? Of E over S. It's a very interesting thing, because first term here depends only on manifold and metric on it. And the second term knows about vector bundle and operator there. So this knows only about manifold, this knows about vector bundle. and the action and blah blah blah. So let me say what is it. A hat of mg is the following series. I over 4 pi of the differential form, which is curvature form for Riemannian metric. So Rg is a differential form, curvature form for G on M. So it has nothing to do with manifold itself. So you take Levi-Civita connection and take its curvature tensor and form two form from this guy. Well, what is the bottom? One, two, three, four, five, six. Okay. Russian citizens are in much more than others, so I write hyperbolic sinus in Russian way. Maybe you can write it this way. Okay, it's denominator. Well, so what is written here? It is a series which starts from this term. Hyperbolic sinus starts from this term. So this fraction is series itself. No problem. Then you can calculate determinant of this guy. It's again series. And more surprising, you can take a square root from that. If you have a series which starts with 1, you can calculate square root from it. Let us check that I'm not lying. So imagine you have f1 plus f2 plus f3, non-homogeneous series. So each term has its own degree. If you take it as squared, then you obtain h1, h2, h3. Let's have a look how to calculate f in terms of h one by one. So first formula is how to calculate f1. So in degree 0 we have 1 is equal to 1, no problem. What we can write in the first degree? 2f1 is equal to h1. So we can find f1. What we can write in the second degree? f1 squared, yes. 2f2. It's equal to h2. Again, we can find f2. What about f3? 2f3 plus f1, f2, 2 times, I guess, yes, from 1 and another way, so it's this one h3, and so on. By induction, you write similar formulas, so you can take, so this series is just square root from this series. It can be defined by induction. Same happens here. Okay, so first term is okay. What has happened to second term? It's more complicated thing. Let me remind you that we have supertrace, relative supertrace, from what? From endomorphisms over Clifford. So we speak about in one fiber. So we have V, we have scalar product there. So we take graded endomorphisms of, why I wrote here V, I don't know, E, okay. Okay, so Clifford M. I want to write it over in general case. So this is a fibration vector bundle. Yes, this is graded endomorphisms over Clifford module, which are commutative with Clifford action. So we take endomorphisms which are linear with respect to multiplying by sections of Clifford M. Then to these sections we can apply supertrace, relative supertrace, and obtain section of trivial one-dimensional vector bundle, so complex valued function. Well, Now imagine we have more complicated thing. So we have differential form with values and graded and endomorphisms of this thing. So if we apply supertrace to each coefficient in differential form, we obtain differential form on M with complex coefficients. Well, and now we...
So on the right hand side you have trivial vector bundle of rank 1, yes?
Here?
Yes.
Yes, because fiber-wise I apply
Trace.
and then you obtain a number, but I obtain a number in each case. It does not depend on orientation, blah, 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 so it cannot be twisted. So this trivial vector bundle. If we have endomorphisms, differential form with values and endomorphisms, then I apply supertrace to coefficients and obtain differential form, complex valued. And now, you can guess that here will be some curvature form. Maybe it's power. So now let me define what is relative Chern character. We apply supertrace to what? To exponent of I over 2 pi of relative curvature. Well, that's all. This term is written here. The only thing we need to understand why curvature. Well, what is relative curvature? So everything else is defined. What is this guy? What is relative curvature? Well, I guess we have half of an hour to calculate it and define. It's not very difficult, but it takes a little bit of differential geometry. It's not a curvature of a connection nabla E. It's a little bit twisted.
What does this bold S stand for?
So, okay, if we have endomorphism which commutes with action of Clifford multiplication, then actually we have endomorphism of module from which this thing was induced by tensoring with spinor space.
So S is spinor space.
S is spinor space. So that's why I forgot to say that M, dimension of M is even. Yes. Okay. Well, I wrote a bunch of formulas which I tried to make as simple as possible, so I need to look for indices because they... Okay, let us remember what is how we defined that this thing and exterior algebra were isomorphic. How we did it. How we defined map from Clifford to exterior algebra. There was a map C of what we did, we took exterior product and then we subtracted interior product with this is a dagger, so this is a metric dual. Yes, this is a map from what? From Clifford. So C is a map from Clifford to endomorphisms of exterior algebra. Well, and if we calculate, so sigma of x,
You denote vector space as lambda big.
It's V.
oh, sorry, it's V. It's V, thanks. V and metric is supposed is given. V is cotangent space at each point. So Clifford maps here. How? First of all, we map Clifford into endomorphisms by this formula. We define the action of one vector, and this map satisfies commutation relations for these things. So then I want to define sigma of x. I define it very simple way. I calculate S of C of x. Actually, this is a symbol for Clifford, and calculate it on 1. For example, if I take EK, then this one is, you can guess what happens. So it's homomorphism, so you need to calculate C of E1, blah, 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 C of EK applied to 1. Look here. Then you calculate C of vector. What you're doing, you take exterior product and internal product. But in 1, there are nothing, no part of 1 can be contracted with this vector. So it's just exterior part. If you take E, I, k minus 1, you have still 2 parts. But this one cannot be contracted with this one. So you again take an exterior product. So it's a very simple thing. You have nothing to contract. You have only exterior powers. This is a very... Okay, so we know. Now I want to define what is inverse. Inverse map.
Is it correct that V goes to V itself, a vector? If V is a vector, then via this sigma...
Yes, that's correct. Q is inverse to sigma. It maps this guy to this guy. Now, tell me please, what can you say me about properties of Q? Okay, this was used to prove that the dimension of Clifford is the same as dimension of exterior algebra, so it's linear isomorphism. Sorry, I asked the question and gave the answer. So it's linear isomorphism. It does not preserve product. These two algebras are not isomorphic. That's why people sometimes say that Clifford is quantization of exterior algebra, because it was skew commutative algebra, and this one is not skew commutative algebra, because sometimes you interchange order of two elements and obtain something else, non-trivial commutator. So this is inverse.
That's why this has value Q.
Yes, sure. Sure. Okay, now I want to define very strange thing. Spin of V as Q of exterior square of V. Why do you think I denote it by spin? We have two spins. One was defined a few lectures ago, and this is another spin. What is the difference between them? That spin was an object of which nature? It can be a function, a linear operator, maybe it's this one. It was a Lie group. It's a group. So you can multiply elements here, but these elements are not multiplied because it's just linear space. Actually, this guy is a tangent space to this one. So if you take an exponent, usual exponent inside Clifford algebra, because in Clifford algebra you can write exponent series in the usual way. You multiply things, divide by factorials, take a sum. So if you apply your exponent to elements from this guy, it takes some time, but you can show that this is an exponent which takes value here. Okay. But we do not need it. So what I want to do next, statement. Spin because I'm writing by hand, let me underline it to show that this is small letters. Small letters. Spin V acts on V. Formula is as follows. You take element here. Notation for the operator is
I can ask a question.
Okay.
If we pull back the lead bracket from spin, from little spin, then it will be just wedge on the
You will
square.
see. You will see. I'm going to tell you about it. A little bit more complicated. It will be commutator. So I need to say how X acts here. X sends V to commutator with X. You will see very nice presentation of algebra SO inside Clifford algebra. So what's happening? So we need to check that actually I wrote a formula, but what I want to prove that it will be tau, that tau of X actually belongs to SO of V. So it's a skew-symmetric operator there. So let's go to check. Okay, it's linear. It's linear, so I need to check that it preserves V just on basis vectors.
I ask stupid question.
Okay. I like stupid questions because usually it's very simple to answer.
We do this operation in
Clifford algebra.
and get a vector.
It's a miracle. It's a miracle, yes. This is first, I already told that I need to check that this guy preserves V. Okay, let's calculate. What I want to do it on basis vectors because everything is linear. So take a product, EI, EJ, so I smaller than J, and take K and calculate commutator. What I want to say that if assume that K is not equal to I and K is not equal to J, what happens to this difference? You need to interchange K with J and then with I. You have change of sign twice. It will be 0. If K is equal to I, it will be a little bit different. EI, EJ, EK minus EK. Okay, I, EI, EJ. What we will see? Yes, minus 2EJ, and if K is equal to J, it will be EI minus something strange. Wait a moment. IJ, K, yes. Oh, sorry, plus, here plus, because product of two these things is minus 1, and also 1 minus here. This will be 2 minus 2 EJ. EI, yes, that's correct. So it means that tau of V preserves V, correct?
Tau of X.
Tau of X preserves V, yes, that's correct.
So we take X, yes, and express it as we have degree 2.
Degree 2, only degree 2, degree 2.
Okay.
So this guy preserves V. I want to say that it's skew-symmetric operator there. How to check it? We need to calculate scalar product of what? Yes? We take action of this guy. Okay, write the commutator. Don't write stupid formulas. EI, EJ, commutator with EK, then scalar product with EM. Oh, M is occupied. EL. And then check what happens if we take EK here and then commutator EI, EJ, EL here. Tell me, please, what you can say about these expressions. We can think that E1 blah 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 En is orthonormal in V for simplicity, because we need to calculate scalar products. Look here. For this commutator to be non-zero, we need to know that K is equal to I or equal to J, otherwise it's zero. For these things not to be zero, we need that L is one of these letters. So the only interesting case is then I is equal to K and J is equal to L. Maybe you can interchange something, but these two pair of indices and that two pair of indices should be the same pair. Now we just calculate it. So if this EI, then this will be 2. And if this is J, then this is minus 2. So that's why we need to write here minus. Okay? So we have skew-symmetric operator. Do you know skew-symmetric operators in some vector space equipped with scalar product? It's operator from SO. Xij is a basis in SO small of V, which is defined by the following formula. Well, now I need to look at my paper because I need to know how it acts here. It sends EI to EJ and EJ to minus EI. So it corresponds to the matrix of this form, which is a generator of Lie algebra SO. So as you can guess, we obtained an isomorphism of two Lie algebras, that one and this one. The map is tau from spin of V to SO of V, which sends EI EJ to 2xij. 2 is not a joke, it's an important number. Okay. What we need to see is we prove that it is an isomorphism of vector spaces. Then it is an isomorphism of vector spaces. Because dimension of this space and that space are the same, we know how basis elements go one to another, so everything is okay. What we need to check to see that it is an isomorphism of Lie algebras, we need to calculate what happens to the bracket on one thing and another thing. It will be an exercise for you. Spin is equipped with a commutator, bracket. So you calculate commutator inside Clifford, AB minus BA, but it's a miracle that commutator of two such elements still belongs to this subspace. Just direct calculation. Or maybe you want to see the proof. No, let it will be an exercise. I have something to ask from you, so it will be an exercise. Okay, So we have obtained isomorphism of vector bundles. We obtained an isomorphism of Lie algebras.
And with this Dirac commutator, it is isomorphic to SO.
Yes, exactly. Well, very good. So now I want to erase this part of and continue here. We almost done, but not yet.
And why we did this? We already know that spin is simply connected.
Actually,
Of SO,
yes,
so we
yes,
have
yes.
isomorphism of-
I need to write a formula for curvature tensor in terms of these elements.
You want to calculate.
Yeah, I need to calculate curvature of the Dirac operator, of general Dirac operator, and if you then we calculate curvature. So let me repeat the problem. If we calculate curvature of connection on a vector of space nabla E, we will see that this guy is not Clifford M linear. It's not Clifford M linear. That's why I cannot apply the construction of relative trace.
Сейчас, то есть вам как будто бы удобнее вот именно с этим, с этим представлением спин V, да, Вася?
Да,
Не с SO, а
именно
вот
с этим. Сейчас увидите. В этом фокус состоит, что вот эта штука, она не является линейным над Клиффордом. Из-за этого я не могу супертрейс применить относительный. Вот эта часть, относительный характер черна просто не определена. Надо сделать следующее. Надо будет взять кривизну вот эту вот, ее чуть-чуть подправить на кривизну того, что происходит в базе. И тогда у меня получится вот эта штукенция вот такого типа, и тогда эта вещь будет корректно определена. Так, окей. Sorry for speaking in Russian. For every matrix which belongs to SOV, we assign differential form. Not a differential form, element of exterior power. In which way? In a very stupid way. So let me write it as a, you know that. So you know that if you have a matrix, you can express it in terms of matrix generators, matrix entries. So how to recover entry of the matrix A? You take matrix, apply to basis vector, and take scalar product with another basis vector. Yes, it's element of the matrix which sits on the place ij. But this guy is Q-symmetric, so you write here generator and take a sum over I smaller than j. So you take a sum of, say, lower triangle part of this matrix X. So having in mind this expression, I define this guy. It's not a consequence, it's my definition. So from this formula, I do not derive another formula. I just write similar formula, which looks as follows. Omega A is equal to J, so the same number. But to have an element from this space, I write here EI wedge EJ. Very simple. Claim. We have two things. One sits here, another one sits there. Please remind, we have three spaces. Spin, we have SO of V, and we have exterior part of. They are related by two homomorphisms. Here goes Q, and there goes tau. What is written here belongs to these two different spaces. So if I want to compare them, I need to go to spin. The claim is as follows. Tau minus 1 of A, which now belongs to spin, and quantization of A, omega A, where should be 1/2? Yes, should be 1/2. Let's check. It's not difficult. How tau minus 1 acts here? It's linear, so we don't worry about coefficients. Then we apply tau minus 1 of xij. Tell me, please, what is xij? Tau minus 1 of xij. It is written on the blackboard.
1/2 of E sub I times E sub J.
Yes. It's 1/2. But from this formula, we see that it is exactly 1/2 of q of omega e. Because then you calculate sigma of a product, you obtain wedge product. Because sigma of ei ej is ei wedge j, and if you calculate this one, you obtain ei ej, because they are inverse one to another. Well, we are almost here. Well, tell me please what we can say about curvature of this connection, where it belongs, what is doing. What is the curvature of the connection? It's two form with values where? Endomorphisms of what? Yes, C endomorphisms, not over functions. Over functions, yes, but they are endomorphisms not on the Clifford sections, but over the functions. Yes, it sits here. And what you tell me about curvature of Levi-Civita connection? They belong to sections of what? Where it acts? Tangent bundle. So it's endomorphisms of tangent bundle. So as you can guess, these are two very different things, yes? Absolutely different. And I want, for some reason, I want to relate them. Okay, let's go. Let's have a look here. This one belongs to sections, not to endomorphisms of Tm, but on specific vector bundle which is constructed from tangent bundle, taking skew-symmetric matrices of that, because the Riemannian connection consists of skew-symmetric operators. Curvature provides us with. So,
I forgot.
sorry?
Should there be omega squared in this case, or it's just SO of Tm?
Please repeat. SO of Tm, it's part of endomorphisms of tangent bundle. If you look at this locally, you will see that endomorphisms are just matrices. And also the same gluing cycle, but matrices are skew-symmetric.
I forgot who is RG.
Curvature of Levi-Civita connection.
Okay.
This is a curvature of connection nabla E, and RG is Levi-Civita connection, blah, blah, blah. Riemannian connection. Well, I want to put it inside something more complicated. So SO of Tm can be identified with, we have metric, so we have SO of T star M. Do you agree? Then we put it inside differential forms of Clifford of M. How we do it? because SO, it is the same as spin. Spin is a part of Clifford, so we sit here, and then we embed it into two forms. Clifford of M, graded tensor product with endomorphisms of E. Okay. So this guide doesn't act here. It works only on sections of this thing. It doesn't act here, only here. Okay. What I want to do, I want to write an expression for this thing in a local frame. Let me do it. So if you consider R as a differential form, it looks as follows. So you apply here. What is written here? It is two covariant derivatives along these two vector fields minus commutator of covariant derivatives along this guy, and also minus covariant derivative along commutator of these two objects, yes? But to obtain differential form, I need to multiply it by these things. Now it's differential form. Okay. But question, where it is? It belongs to omega 2 of SO of Tn. But I want to embed it here. So I need another expression for that. How to do it? First of all, I need to pass to metric dual and then take embedding. So what are dual to these vectors? Metric dual. Yes, so denote EI dual basis for EI. So it will be differential form now. Well, I think, well, I'm very, very sorry why I wrote this. I calculate this one, and I should write differential form here immediately. Okay, that it will be correct from the beginning. Okay. So how? Okay, where is an operator? This is an expression which consists of several parts. Where is an operator?
An operator from SO?
Yes.
RE.
This is an operator. Okay. This is an operator. So from SO we pass to well, how to denote it for simplicity? Okay, so I erased here. So the action of vectors on exterior algebra should be given by this formula. So after all these embeddings, this guy should look like this. With 1/2, because 1/2 comes from here. And then we write something like 1/4. Sum is not needed now anymore because this is skew-symmetric and this is skew-symmetric. Okay. So now, I'm not happy about that. I'm not very happy about this thing. No, what I want to do, I need to calculate this thing on a pair of vectors. How we do it? C goes from where to where? Yes. So this sits in Clifford, yes. It sits in Clifford, and now after all these procedures, this guy sits here. So what I'm doing, I'm taking C of, so this would be differential form. So this is doing the following thing. So if I substitute these things, so there should be something like that. We apply operator to the first vector, take scalar product with another vector, and then write here C of EK, C of EL. Yes, now I like it much more. And I'm afraid I need to write here some multiple. Well, okay, now because it's everything is skew-symmetric, I can write well, now I write the following thing: 1/4 EI, EJ, EK, scalar product with EL. I usually I write here G, so well, now I'm happy more or less. So this is a formula for this operator.
Maybe to be explicit, we need just to use this claim we wrote, because EI, EJ is Q of something.
Yes,
right?
yes.
Replace it by E tau.
Yes. Oh, sorry, we took too much time. So do you have, say, 10 minutes? Okay, we just need to finish. What I want to say, if I, so definition. The curvature, relative curvature, the thing which is linear over Clifford over action of Clifford is as follows. We take curvature of the connection nabla E and we subtract from here C of R, the thing which is defined there. Let me, so this will belong to differential forms with of this guy and the morphisms of E. And what is important here, F ES is coM linear. Thus it has well-defined relative supertrace. So roughly speaking, we can say that FES belongs to endomorphisms over Clifford of M of E. Yes? Oh, not correct, differential form. Every time I forget about differential forms. Let us calculate it. So we need to check that in the following proof. We need to check the commutator of this guy with action of 1. So Clifford of M vector this bundle is generated by sections of this type. So by alpha is one form. So we need to check that this commutator is 0. To calculate this commutator, we need only one thing. We need to calculate commutator with C alpha of this part and that part. So let's go. Let's go. Nabla E of xi of C alpha of U is equal. Tell me please, what is it? How to calculate it?
By our formula.
By formula from the definition of Dirac bundle. So we need to take C of nabla G along psi of alpha, then apply U, and plus what? C alpha applied to covariant derivative along U. So this is one. So if from this it follows that if you
It is Clifford linear, yes?
sorry,
Now we prove that it is Clifford linear, yes?
we want to prove that this is true. So this definition. Oh well, sorry, it's definition theorem.
We don't prove that it is linear. Or we do
It's not linear.
Clifford linear.
It's not Clifford linear. One covariant derivative is not Clifford linear.
No, I ask about we write proof for what?
We're trying to prove this one.
For the theorem, yes?
Yes. But this thing consists of several building blocks.
Okay.
And I want to start from this one. So if I calculate a covariant derivative of this thing, I obtain this one. So now I know that if I take commutator of covariant derivative in E along vector field xi with C of alpha, it is a very simple operator. Because this thing consists of two these things. It's just Clifford action applied to where? To this thing. It is not a derivative of vector of a section U. It's covariant derivative of vector of one form alpha. Tell me please what you will see here.
The same.
The same thing, but with commutator. From these two formulas, we should obtain something very simple, that curvature of the connection E calculated on two vector fields xi and eta, and after taking commutator with alpha is what? On section U. What is it? Let me check if I write it correctly. Yes. What do you think about that? So this is a formula for what? This is a formula for one single covariant derivative. Yes, then you apply another single covariant derivative, then nabla xi, nabla eta in different order, then you take into account.
Там будет covariant derivative вот этой G. C и F от связности.
So? C of what? Of R, no F, because you see that taking commutator of Clifford action with covariant derivative in E, you obtain covariant derivative in manifold itself. So here you have curvature RG. So we wrote G here. But to be honest, the curvature acts on where? Curvature acts on vectors, and alpha is differential form. So I write here metric dual. Okay? So this thing itself does not commute with Clifford action. It gives us this result. But what is a miracle? Miracle is more or less. Yes, more or less. What you need to understand that the thing which is written here, it is exactly C of RG. Check it. Just play with isomorphisms, left, right, and so on. The isomorphisms which are written there. From time to time I write R or RG, it is the same. So this one is RG. Curvature of Riemannian curvature on manifold itself. My congratulations, we know all the ingredients of Atiyah-Zinger theorem. That's all for today. So theorem is proved, so we know all ingredients of curvature, of the right-hand side of the Atiyah-Zinger theorem, and you have something to exercise at home.